All right, so we're going to finish up section 4.2, basically looking at changing which part of the fraction now has the higher exponent. Okay, yesterday, it was always the denominator that had the higher exponent, or they were equal. Okay, so that's what we did yesterday. Okay, today we're going to look at what happens when the degree of the numerator is larger. Right? So when the degree of the numerator is larger, we can start to get asymptotes that are curved, and the only way to find them is long division. So we're going to have to use long division from what we learned last week. Most of the time, synthetic won't work unless you're dividing by something that's x minus a number. Okay? But if not, we've got to use long division. So this is something that really only applies to the stuff we're learning today. When the degree of the numerator is larger than the denominator. We have a new thing called an EBA, end behavior asymptote. So suppose that we had a rational function, and we're going to divide it, okay, just like all the problems we did yesterday. Now, h of x is going to have a bigger degree than g of x. To find the EBA, you don't have to do anything new that you haven't done before. We're going to just reuse something we learned last week. When you divide these, you're going to get two parts to the answer. You're going to get a quotient, and you're going to get a remainder. Well, we talked about this last week. When you divide two things, you can write your answer as quotient plus remainder over the original denominator. Just like if I were to do like, let's see, 13 divided by 5. The quotient is 2, the remainder is 3. I can write my answer as quotient plus remainder over original denominator. And if I did everything correct, this should equal the original problem. And it does. 2 3/5 is the same as 13/5. Okay? That's what this part is saying right here. Well, the only part that you really care about when you're doing the EBA is the quotient. We don't care about the remainder part. So basically, the EBA is the quotient when you do long division. That's all. Any question on that idea? Now, the way you can tell how bad the asymptote is going to end up being is when you look at a problem and you compare the exponent in the top, the biggest one, to the biggest one in the bottom. Okay? The top is a degree 3, the bottom is a degree 1. This EBA is going to be a degree 2. Okay? The further apart these are, the worse it gets. Yeah.
So that right there, we could use synthetic division.
You could. Yep. That would work with synthetic division. So we'll get to that one in a little bit. Well, actually, now is a little bit. So let's take a look at finding the quotient, the remainder, and the EBA. Now, does anybody want me to do it with long division? Because you will have some that don't work with synthetic. Do it with long? Okay. I mean, we're going to have to practice long division, I think, on that one. Actually, this one. So, yeah, they want the EBA here, so we're going to have to do long division anyway, eventually. So we'll just do one with synthetic and see what happens. What number goes on the outside?
2.
2. And then my coefficients on the inside?
2, -4, 0.
Yep, don't forget the 0 for that x term. Okay, so let's see what we got. Bring down the 2. 2 times 2 is 4. Add them up. 0. 2 times 0 is 0. Put the answer in the third column. Add them up. 2 times 0 is 0. Put the answer in the fourth column. Add them up. Okay. So, let's start with my quotient. What's my quotient here? 2x squared. What is my remainder?
We don't have one.
3.
My bad.
Remainder is 3. What is my EBA?
2x plus 3 plus 3 over x.
Well, so that's that whole formula, but which part of it do we just want to focus on?
I'll put first two. Nice.
Just the quotient.
2x.
Okay, so the EBA is the quotient. This whole formula is true, but we just don't want that other part. Okay, EBA is just 2x squared. Now, the reason we don't look at the remainder part, let me write down what you just said. Let's just look at it. Quotient plus remainder over my original denominator was x minus 2. Look at this is the remainder part. Look at this fraction. As x gets really big, what happens to what I just circled? It gets closer to 0. That's why it doesn't matter. If x is 1,000,000, you have 3 divided by 999,998. That's an extremely small number. And the bigger and bigger that x gets, the less and less important that part becomes. And this is the only part that really matters. Okay? So actually, I think that was my next question. What happens to the remainder, the part that I circled, as x gets really, really big? It goes to 0. Okay, so the remainder part approaches 0. Whether you go to a really big positive number or a really big negative number, it's going to approach 0 either way. Okay. Any questions on that? Quotient, remainder, EDA. All right. We're actually going to be sketching this one eventually. So we're kind of building up to sketching it by doing everything we need in pieces. All right. So first of all, there's a difference between an EBM and an EBA. EBM is super easy to find. You just take the highest degree term in the top, divide by the highest degree term in the bottom. That's the EBM. The EBA, a little more complicated to find. It only applies when the degree in the top is larger, and you have to use long or synthetic division. Sometimes the EBM and the EBA could come out the same. Depends on the problem. Sometimes they could come out different. Okay, so sometimes they're the same, sometimes they're different. So, in all the problems we did yesterday, the degree of the numerator was always less than or equal to the degree of the denominator. We always had straight line asymptotes. Sometimes they were vertical, sometimes they were horizontal. We had both, but they were always straight lines. Now, if the degree in the numerator is not, or if the degree in the numerator is larger, okay, so we don't have straight line asymptotes, what can happen is they can curve. So if they're not straight, they can curve. There's still one case that they can be straight, but they could be on a slant. Okay, we'll look at one of those. So we're probably going to look at a slant, and we're going to look at a curve. We'll do one of each.
So they can be curved, but they won't always be.
Right, you got to look at the top and the bottom and see how far apart are the exponents. If the highest exponent in the top is only 1 away from the highest exponent in the bottom, it's not going to curve. So like if you had x to the 6th minus 4x plus 2 divided by x to the 5th minus 5, that's not going to have a curved asymptote. The degree in the top is 6, the degree in the bottom is 5. The difference is 1. You're going to have a degree 1 asymptote, which is a diagonal line. So it's like y equals mx plus b. What would it be? Do out the long division and you can find it. Now, if I did something like this, the degree in the top is 6, degree in the bottom is 4. That's a difference of 2. you're going to have a quadratic asymptote, okay, degree 2. So the further apart these exponents get, the worse it is. You're never going to have one that are more than 2 apart. Okay, quadratic is the worst one that we're going to do. Okay, so let's verify what we just did in example 5. I'm going to graph this. I'm going to graph 2x squared, and let's see if f of x is really approaching this EBA. Because this EBA we just found, 2x squared, that's a curved asymptote. It's a parabola. Okay, so to do that, I need my scroll bar on the same side as where I am. That would be helpful. And let's type in the original problem. Can somebody remind me, what was the numerator? 2x squared. What was it, 2x squared? 2x to the third, yeah. 2x cubed, yep.
Minus 4x squared.
4x squared, okay.
Plus 3.
Plus 3. And was it x minus 2 in the bottom?
Yes.
Okay. So let's graph that. And let's graph the EBA. Now, when you hit graph on y1, something weird is going to happen at 2. 2 would cause you to divide by 0. So this is not going to be a nice connected graph. So let's take graph and see what happens. Might have to zoom out. Maybe not. Yeah, we got to go a little higher on the y-max, just so you can see the other side. But you know what? Actually, while I have it like this, I can kind of show you. Can you see how the red is my asymptote? The blue is my graph. Can everybody see how the red and the blue are getting closer and closer together? Mm-hmm. So the blue graph is getting closer and closer to that red curve. Now, you don't see the other part because we didn't go high enough. So if you set your y-max to like 25, let's see. We should see the graph in blue start to pop out back on the other side somewhere. There it is. And then the asymptote's going to be sketched. And again, you can see on the right side, if I make it bigger, the graph in blue is getting closer and closer to the graph in red. Okay. It's not a parabola because there's this weird vertical asymptote in here. So it's like you took the parabola and it's like you broke it apart at that asymptote and you bent part of it down and the other part is bending up. It's not connected anymore. Right? Because connecting it, you couldn't have divide by 0. So we're gonna try to sketch that, and I'll show you how to do it. Okay, so we confirmed that our graph 2x squared is a good EBA. Looks like it's getting closer and closer to it. So from the information we have, now let's try to make a sketch. Okay, first thing I would want to find are the asymptotes. When the degree in the top is larger than the degree in the bottom, you don't have to worry about having a horizontal asymptote. You won't. Horizontal asymptotes are gone today. Slant asymptotes and curved are taking the place of them. Verticals, yes. We're still going to have verticals. What's the vertical asymptote here? 2. Next up would be to find the EBA. We already did that. What was our EBA?
2x squared.
2x squared. Okay, x-intercept is going to be kind of hard to find. Because the x-intercept is when you set this equal to 0. And now you have a cubic equal to 0. That's going to be really challenging to solve. If it was a quadratic, I could do it. Maybe I could factor it. But since that's a cubic we're not going to worry about finding the y-intercept here. Okay. But let's try to see if we can do the x-intercept. If you plug 0 into the top, what do you get?
3.
3.
3.
And if you plug 0 into the bottom?
-2.
-2. So my x-intercept is at negative 1.5. Okay, so let's graph that. It's going to cross right there. Let's sketch our vertical asymptote. Alright, so I'm going to put that in. It's going to make it a little smaller. Alright, put that in at 2. And I'm just going to extend that. Alright, now to sketch the EBA, if you get stuck, what I do is you could just make a table of values. When x is 0 and you plug it in, what do you get for the EBA? 0. How about when x is 1? 2. When x is 2? 8. 3, yeah, 3 will fit. When you get 3? 18. And it's symmetrical because it's a parabola. So -1 is also 2. -2 is 8. -3 is 18. So let's sketch those. You know what? I'll do my asymptote in green just to match the other green one. So 0, 0. 1, 2. 2, 8. 3, 18. And then just mirror it. So we got here, here, and I gotta go one more. There we go. Okay, and now draw that as an asymptote. So the way I'm going to do it, I'm just going to make it solid, and I'll change it to dotted after. Okay, let's go here, and then make it dotted. Okay, so those are my 2 asymptotes. Now, just like always, let's check what's happening on each side of the vertical asymptote at 2. Alright, so we've already got it typed in. What's a number that's a little bit smaller than 2?
1.999.
Yeah, let's go 1.999. We're at negative 3,000. So just before the asymptote, you are dropping almost straight down. Let's see what happens just after. What's a number that's a little bigger than 2? 2.001. Just after my asymptote, I'm going way up. I'm at 3,000. So I'm way up here. Now, I know this is going to be in 2 pieces because I can't cross this vertical asymptote, right? But I have a dot on the right of it and I have dots on the left of it. I need a couple more dots. Okay, I can't really tell what's happening. So let's put in, I don't know, what do you think a good x value would be to get the left part of this graph? -2? Is that what we said? All right, let's do -2. And I'm at 7.25. So -2. I'm at, should be up, I don't know, right about, oops, I erased part of it. But right about there. Okay. My parabola is not perfect. It shouldn't cross that dotted line.
It's because you shifted over.
Yeah, it's at -3.
That top dot's at -4 right now. You gotta change that. You gotta put it.
Oh, it's supposed to be.
And then your
It's supposed to be 1 to the right.
Yeah, so let's
You
double check.
shifted your negatives 1 to the right.
-1. So this dot should be
It should be at -2 rather than -3.
-2. It should be right there.
Yeah.
Yeah.
And then you also shifted your other side, I think.
1, 2,
but-
3, 1, 2, 3. That's why. All right. So if you drew yours correctly, I just messed up a little bit. So that looks better. All right, so now we had, what was it, negative 2, 7.25. So negative 2, 7.25, perfect, right about there. All right, you can keep getting more red dots, but it's just going to keep staying very close to that dotted green edge. Yeah. Let's try 0. I think 0 might be a good one. 0, negative 1.5. So let's see, we're going by 2s. So negative 1.5 is like right there. Let's also do 1. Negative 1. So 1, negative 1. Remember, I'm going by 2, so it's halfway. All right, I got enough. So it's basically going to stay right near that. It's going to start moving away from it. It's going to curve and then stay right up against that. Now, the other part of the parabola, this can be the part that's a little tricky because it was off the screen. We didn't necessarily see it right away. It's going to be trapped in this small little section here. It's got to stay right up against that. And it can't cross that other dotted line. But it has to somehow move over and start getting next to it. So the only way it can do that is if it comes down, it curves, and then almost makes like a U-turn. So if you want, you can get a couple more points. Let's try 2.5, but I don't know if we're going to be able to do it. 18.5. So 2.5 is 18.5. So right in there. Now, I don't think I can do 3. I think 3 is already going to be way off my graph. Well, I can still kind of do it. So 3 is up at 21. If I try to go any bigger, like 4 or 5, now I'm at 51. So this thing it's going up real quick. So it goes through these dots, comes down, kind of turns, and goes back up. And if we graph it, that's exactly what you pretty much saw. Okay. So plotting points is really helpful. It kind of helps me a lot. But that's the worst one that we look at. Okay, any questions about what I did there? Now, why was this a quadratic EDA? How could you tell that it was going to be a quadratic right away? Adrian?
Because it's about the difference of the two greatest powers in the denominator.
And what's the biggest one in the bottom?
1.
1. And the biggest one in the top is a 3. The difference is a 2. Okay. All right, let's look at this one. So this is the one I told you we're going to have to do long division anyway, and that's right now. What's going to be the degree on the EDA?
1.
It's a degree 1. Degree 1 is a y equals mx plus b equation. Not x squared or anything like that. It's just mx plus b. So that's what we're looking for here. We could probably do the verticals right away. We'll get those out of the way. So let's do the vertical asymptotes. Okay, how do I find vertical asymptotes? Matt?
Setting y as 0.
That would give me my x-intercepts.
Oh, yeah.
If you made this 0.
You gotta. The bottom has to equal 0. Right?
Yes, and what would we really want to do to the bottom to make that simple?
Oh, factor it.
We'd want to factor it.
1 and -1.
If you can't factor it, you're going to have to use quadratic formula. So x, Derek said 1 and -1.
You want to add 1 instead of that, right? Or add 3.
Wait,
Yeah, you want, so x plus 3, x minus 1.
Yeah. Wait. Yeah, that's right.
Let's try
X plus 3.
that. X squared plus 3x minus x is 2x. Perfect. Don't even worry about the numerator. That's fine. So what are my vertical asymptotes here?
1 and -1.
1 and -3. Okay, let's put those in. So we got 1 and negative 3. There's 1. There's negative 3. Okay, so we got that. Now they want the EBA. So the EBA is just your what?
Your quotient.
It's the quotient. Yeah, the degree of it will be if you subtract the two highest exponents. But what is it actually? Like, is it 5x plus 6? Like, what is it? We got to do long division. All right. I'm going to do it on a separate page. So x squared plus 2x minus 3. Into 2x cubed. Might need help. 2x cubed plus 7x squared plus 0x. What was the constant?
-4.
-4. Now remember, we don't care about the remainder. Once you get the quotient, we're done. Okay. What's 2x cubed divided by x squared?
2x.
2x. So we already have the mx in our mx plus b. Multiply it back out. We're going to get 2x cubed. 2x times 2x.
4x squared.
And 2x times negative 3. 6x. And what do we do with all that? Subtract. That's gone. 7x squared minus 4x squared. 0x minus 6x.
Plus 6x.
And you can bring down the -4, but it doesn't even matter. We're basically done at this step. What's 3x squared divided by x squared?
It was 3. Yeah, plus 3.
Plus 3. There's your quotient.
So you can just stop now.
Yeah, if you kept going, you'd be finding the remainder. So your quotient is 2x plus 3. So what's my EBA?
2x plus 3.
Yeah, 2x plus 3. Yeah.
What did we say that the remainder found? Like if on the like one of the first couple pages, first couple slides.
The remainder?
Yeah, I thought like you could do something.
So it's, you can write your answer as quotient plus remainder over denominator.
What was on the next slide? Figure that. I feel like we did something with that. Maybe not. Maybe not. Oh, was it defined? Oh yeah, it was defined what happens to the remainder when it goes to positive.
Right, if you were to keep writing this out, the remainder wouldn't matter because you'd have an x in the bottom,
Okay, yeah, that's what I was thinking.
and it wouldn't matter. Okay, so we got our verticals. This is pretty straightforward to sketch. Just plot your y-intercept. And my slope, what does that mean I do from the y-intercept?
Every 2.
So like, which way am I going to go to get more points?
Right.
Up to
Up 2 and then
over.
right 1. So up 2, right 1. And we could also go down 2 and left 1. As long as I'm straight here. Let's put the dotted line in. So about like that. Don't move your graph. See if we can move that right there. Okay, so let's start checking some points. Okay, when I check some points, it's going to tell me, okay, am I up in the top part or am I down in the bottom part? Because I basically have 6 sections here. 1, 2, 3, 4, 5, 6. Usually you end up drawing in 3 out of the 6. This is kind of like yesterday. All right, so my first asymptote was at, I think I moved this just a little, but it's okay. Did I type it in yet? Once I type it in, no. I need the number a little smaller. So let's do 2x cubed plus 7x squared minus 4. Divided by x squared plus 2x minus 3. Okay, What's a number that's a little bit smaller than -3? Yep, so -3.001. One of two things is going to happen. It's either going to be way up high or it's going to be way down low. It's way up high. So put a dot way up high. Now, let's check just to the right. What's a point a little bit bigger than -3? -2.999. Usually if one side is up very high, the other side is down very low. So -1200. So you are way down here. Let's check our other one. What would be another good number to type in?
0.
0 would be good for just a point to plot. But let's check our asymptote first. But 0 would be good eventually. Yep.
0.999.
Yep, 0.9999. And I am down very low, -12,000. And we can check the other one, but we're going to be up very high, 1.001. We're up at positive 1,200. All right, so way up here. Okay. Now, if you're still not sure what's happening, what would be another good point you could check in the left section? Yeah, I think -4 would be a good one. It's small enough that it's still going to fit on my graph. -4, 2.5 is a point. So -1, 2, 3, 4, 1, 2.5. Oh, why am I looking at 2.5? -4, -4, thank you. 4, 1, 2, 3, 4. All right. Let's even do -5, and then I think you'll get the idea. -5, -6.5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6.5. So what's happening is it's basically going to curve, stay very close to that green line. Okay, so it's very close. Starts coming away from it. And then gets closer and closer. Okay, the middle. I don't have enough there. All I can tell is this. It's going to do something like that. What's another good point? I think someone, Vinny, maybe you said it?
Yeah, 0.
Yeah, I think 0 is good. So 0, 1 1/3. Right there. Let's do -1. Let's check that one. -1, -1/4. So -1, -1/4. All right, so basically what's going to happen here is it's going to go up. Wants to go up, but it has to turn. And then at some point, it's going to turn back to go through those. Exactly where is this maximum? That's a local maximum in there. I don't know exactly. That's fine. Okay, and then this last section. Well, I can tell this. It's definitely going to do that. What would be maybe one other good point to check?
2.
Yeah, I think 2 would be good. 2, 8. So 2, 8. I think if you check 3, I have a feeling it's going to be above 10, so it's going to be off my graph. No, I just barely, right on the top of it. 3, 9.5. 2, 3. So right about there. Okay, so it's going to do something like this. And that's what your graph should look like. Let's graph it, but let's set the Ymax a little higher than 10, because right now if I graph it in a standard window, what I circled is all you would see at the top. It's going to cut off everything else.
Maybe like 15.
Yeah, let's try like 15. I guess 25 would be okay, but let's just try 15. Alright, let's see what we got. So remember, it's always going to draw left to right. So you gotta. Not bad. It's pretty, I mean, the left
Close
section.
enough.
What's that?
Close enough.
Yeah, it's close enough.
That's cool.
That's what it looks like. So, this asymptote, a little bit easier to deal with, at least sketching, because it was just y equals mx plus b. Not as bad as a quadratic. And does anyone remember what I called it? What kind of asymptote? A what?
End behavior asymptote?
It is an end behavior, but like the other one we did was a quadratic EBA. This one is linear, and it's on a slant. Yeah. So this is called a slant asymptote.
On the test, are we gonna have actual like graph paper to do it on, or are we gonna have to make our own?
Yep, you will have graph paper.
Okay.
Yeah. Okay. Any question on that one? So don't expect to know what these things are going to look like. It's not like a parabola that's nice and simple and you can tell what's going to happen. I can't look at that and tell that it's going to do all that stuff. I just have to graph it, put the asymptotes, and check some points. I'm going to hold off on that one, but if I were to do it, could I use synthetic division to find the EBA?
Yes.
Yeah, sure.
What number would be on the outside?
-2.
-2. What kind of EBA would it be? It would be a slant. Top is degree 2, bottom is degree 1. How many vertical asymptotes? Just one. Okay? So what that's going to look like is something kind of like this. One vertical, one slant, and you'll probably end up sketching in one section like that, and one section like that.
If there's only one.
If there's only one, yep. I mean, I guess you could be inside
Someone going like this.
those two sections.
It looks like someone standing on one foot.
But my
just,
guess
like,
would be you're-
spread out like a starfish.
You're going to be in that kind of look. You can graph that and check.
Alright.
All right, let's, okay, this one is just a graph on the calculator. I just want to graph it and see what happens. And I want to find the complete graph. Okay, meaning show me anything that's important. So let's type it in and see what happens. Good. 2x to the fourth plus 7x cubed plus 7x squared plus 2x. What kind of asymptote?
Slant.
Yeah, I'm looking for a slant, EBA. Maybe a vertical asymptote, I don't know. That'd be very challenging by hand, which is why I'm not having to do it by hand. Because you'd be trying to set a cubic equal to 0. Okay, so we're not, I mean, you could, you'd have to do the rational root theorem and all that stuff. But we're just going to graph it and see what happens. So we got x cubed minus x plus 50. Okay, and I'm going to start with zoom 6. So you should expect to see a slant asymptote. And it kind of looks like, yeah. Well, I'm not really seeing the slant there. So what I'm going to do is I'm going to just go out a little higher and lower. And see, because it almost looks like it's curving away from a slant, which is not what you want. Speed it up a little bit. Let's see if it starts to curve. Yeah, now I can see it. I couldn't see this off the screen. It is starting to curve back. So I would say, if you were going to put a line in there, your slant asymptote might be kind of like, I'm a little off, but kind of like that. Do people kind of see it?
So if you went further out, you'd probably be able to see it more.
Yeah, it would even get closer and closer. I think my slope is a little too steep. My slope should come down a little bit. Okay, so that's a good big picture. But look at that graph carefully. Is there anything that looks suspicious about that graph? Everything?
It's kind of visual.
It what?
Flattens out.
It looks like it flattens out. So let's check and see what's happening here. Okay? So what I'm going to do is, instead of going negative 25 to 25, okay, that's a good window that shows you the big picture. Let's basically zoom in on like that section right there. So that's going to be like maybe negative 2 to 2. And let's see what we're looking at. All right, so we zoomed in to that section. We get that graph. Can we really tell anything there?
Can we go closer?
Let's go even closer. Let's zoom in
Right there.
on that. So now I'm going to set it from like negative 1, 2, 3, negative 4 to 2 on the x's. Okay, just to zoom in a little tighter. And how about on the y's? What should I try?
0.5.
0.5?
5.
Let's go like 0.1. Let's go, because that's so close to the line. We're going to go negative 0.1 to 0.1. So we're zoomed in pretty tight now. Let's see what it looks like. So, is it flat? No. So my point here showing you is sometimes to find a complete graph for this problem, you would actually need 2 windows. I would say this is a good like big picture view where you can see the slant asymptote and the vertical asymptote, but you can't really see what's going on here. So if I was giving a complete graph, I would give both of these. The big picture, mins and maxes, and then show me zoomed in. Okay, so to me it looks like that actually crosses 4 times. You might want to zoom in a little more, but I think I can tell it's 4. Okay. Any questions on that? Okay, so the point of that problem, not really to do anything by hand. Just that if you graph something, even though you might think it's flat or whatever, zoom in and check it out. Okay, any questions on that?
I had one all day.
All right.
Dude, I've had it for like a day and a half, and it's the worst thing ever.
Okay, so homework tonight, same section as last night.
It's like, I'm not sick enough to justify not coming to school, but I'm also like sick enough that it's not.
Again, last homework for the term. So tomorrow, after class, I will be updating your homework average. So it'll give you a better idea of your term grade. And then on Friday, once I grade your test, I'll put that in as well.